Hello everyone, and welcome to another Jura video, which is my programming language that I'm making in Java that compiles to Java bytecode, because why not? And last time we implemented the simple expression evaluator. So we take a expression like this, and we tokenize it using our lexer. We then parse it with our parser, which is all the way over here for some reason, which structures those tokens. And then we take the expressions that it makes and we feed it to a bytecode emitter, and that outputs Java bytecode, which we then can run. So apparently the output of this is 2. Let's check that. So we run this, and there's 2. So we have a working expression evaluator, but programming languages aren't just expressions; they are statements. Languages like this that I'm trying to make are a list of statements. And what is a statement? Good question. They are things that don't return a value. So I don't know how rigorous of a definition this is, but an expression, at least in this language, is going to be anything that will return a value. So this is an expression because it returns the value 2. But let's say I was to put, a semicolon after it. This then makes a statement which doesn't return anything. Or, you could have an if. An if statement doesn't return anything. A while loop doesn't return anything. And so on and so on. An assignment? Well, this part of the assignment is an expression in Java, and this actually returns the value of the lexer, I believe? Or at least this part returns the value. It doesn't matter. You'll see as we get to it. Today I'm adding statements, if it wasn't already clear. Since last episode, I've gone and tidied things up just a little bit without having to worry about doing it live. So I've made expression a sealed class that implements this interface spannable. And what spannable is it just has a method getSpan, and what a span is just an offset and a length. And you can construct a span from 2 spannables. The reason it's an interface is because a token is spannable and an expression is spannable. And so if you take a look at, say, a binary expression, it needs to implement getSpan, but it's just the span from the left-hand side to the right-hand side. So if it was an int expression, its span is just, you have to hand it a span, and we get the span from its token. I think maybe it would be nicer if it just got the token, maybe, rather than having to unpack it like this, but it's kind of semantics, really. You kind of then just parse it once, I guess. So that's all the change I really made. And the reason I made it a sealed class instead of what it was before is because in the bytecode emitter, you can now switch on an expression directly. So you don't have to say switch on the kind. You notice I've gotten rid of expression kind. Oh, I haven't got rid of expression kind. I can get rid of expression kind. And I can now just switch on the expression directly, and the compiler knows all of the cases that it can be. And if I added a new case, this, I believe, would no longer compile, or I would at least get a warning, because it doesn't actually return anything. I think I just get a warning, which is handy, because if I add a new expression, it then kind of highlights all of the places where I have not added the handling for it. So, very cool. So let's add statements. So how are we going to approach this? I think we're going to... Oh, I need to change my keyboard to US because I have a US keyboard for some reason. There we go. So let's use one of these bad boys. So let's actually have 2 statements. And let's make them different. Like this. So currently, if I was to try and send this through the compiler, it's going to complain that it doesn't know what a semicolon is. Unexpected character, semicolon. Yes. Oh, and the reason why I have these spans is because when it comes to reporting errors, rather than using exceptions like this that halts the compilation, I'm just going to store a list of compiler errors with a span, and then you can then build a link that you can click that takes you to the location in the code where that error originated. So let's add a semicolon to our language. In fact, I'm going to take a quick break and then we're going to do that. Okay, so let's add semicolons. So I've cleared this up a little bit. Now it's really easy to just add a new character. We need to add a new token kind, which is semicolon. And you may be wondering, if you can make any language you want, why are you adding semicolons? And it's a good question. I think in this language, what I might end up doing is making semicolons optional in when there's one expression per line. If you put multiple expressions on the same line, you need to put semicolons. I think that's an interesting way to do it. Maybe it's more annoying to read or more annoying to write, because then you have to put semicolons sometimes and you don't other times, but like for the most part you should only be putting one expression per line. But for now, for the ease of compilation, I'm going to say semicolons are mandatory, and then we can relax that later when we realize, where in the code we can detect that there should be a semicolon, but there isn't, and then just insert one internally anyway. But for now, our compiler is done. So if we see a semicolon, that is a semicolon. Cool. How do we parse a statement? Well, our parser currently, if we say parse, it gives us an expression. But actually this should give us a statement, and we don't actually have statements yet. So let's create a statements package with basically the same kind of structure that we have for expressions. So if you have a look at how we do expressions, we have this public abstract sealed class that implements spannable and permits a bunch of these things. If we do the same thing, we need to have a implementing subclass. So what kind of statement is this? I believe you can do that in... You can't do that in Java. Not a statement. But you can kind of do something similar where you just have an expression and then a semicolon, because I can say main. That this is an expression. It's a different kind of expression, and then I put a semicolon after it, and it makes it into a statement. So what that is, or what I've seen it called, is an expression statement, where it is just an expression with a semicolon on the end. And I think that's the easiest way we're going to get going here. I can't remember the syntax for how you do this. It has to be final. Okay. I knew you needed some kind of modifier here to allow it to extend statement, and then you need to add it to the permits and implement the methods. And so this is going to have an expression in it and a getter. I still haven't added lombok, so we're going to have to do this the old-fashioned way. I can't remember my keybinds. There we go. Why is this complaining? Oh, because this is now a statement. And the bytecode emitter now needs to emit statements. What did you import? Well, what did you import? Oh, you didn't. There we go. So we basically for this, we need to look at what the next token is to determine what kind of statement we're parsing. So like most statements begin with some sort of like sentinel token, like if means you're starting to parse an if statement, while means a while statement, and so on. But in the default case, you're parsing an expression. So that could be like an identifier means you're about to call a function, or I mean that's kind of like the only one I can think of off the top of my head. We can make it really open, and then as that causes problems, we can restrict. So I'm just going to say tokens get cursor, and then we just switch on the token kind. But we don't have any special tokens yet, so we will just do this. So you know what? var expression equals that. And then we want to expect a semicolon. So we're literally going to say expect next token kind semicolon. And so you can see this is the part of the code that actually expects a semicolon. We don't have to do that, you know. We can just say you gave us an expression and we assume there's a semicolon and we move on. But for now, this makes it a lot easier to handle statements. So then we can just say var statement equals, in fact, we can just say var statement equals, and then we can yield a new expression statement with the expression. And we should also pass it the semicolon, because then we can have the span. Yeah, we never actually filled this in. So we want a span from the expression to the semicolon. And because they both implement spannable, that just works. I don't think we ever want to have a getter for the semicolon, because we don't ever want to use it for anything. So then that's the statement. In fact, we don't even need to save it anywhere. We can just return switch. Cool. Just like that. So in here, instead of doing just one parse and then putting it into a list, let's just copy what we do for tokens and just do a bunch of this. I know this probably isn't the best way. Like in a perfect world, this would just implement iterable and I wouldn't have to do any of this, but I can't be bothered to figure that out right now. So then we just hand it the statements. And why is this complaining? Because I never updated it. So this has an iterable of statements. And this is going to change once more once we add type checking, because then we're going to have separate like typed statements and typed expressions. But we're not worrying about types just yet. So we want to simply just iterate our statements. So we want to emit a statement. So we want to keep this method because it's very useful to emit expressions. In fact, we definitely need to be able to emit expressions. But now we're just going to add a separate one which emits a statement. And then we can just switch, because it's another sealed class, we can just do this. And I will say for a expression statement, this is where we could do the wrapping of printing it. Because just an expression statement on its own currently isn't going to do anything and we won't be able to see it working. There we go. So for every statement, we just emit the statement. If it's an expression statement, we begin to emit printing, and then we just say, oh, emit with this method visitor the expression inside the statement. Cool. I think that's it. So now we have these two statements. So this one evaluated to 2. This one is going to evaluate to... let's move my phone away. This one's going to evaluate to 5 times 6 is 30, yes, to 34. So we should see it print 2 and then 34. Let me check. Do I do print line? I do, so they should be on separate lines. So we compile that program, and then 2 and 34. Yes, that's correct. I don't know why. When I looked at that, it looked wrong. So we can have more things. We can have 7 minus 5 in brackets. So what would that be? That'd be 2 times 6 is 12. Cool. So now we can have multiple expressions split by semicolons, and they don't even have to be on new lines or anything, because the semicolon is what tells us that it's different. In fact, to prove that it still works, let me do take away 3, so this is now 4 times 2. So it should print 8. There we go. So what I was saying earlier is, like, this should be how you do expressions on the same line, and then if you do this sort of thing, you would no longer need the semicolons. So let's try that actually. Let's see if we can make that compile. So in our parser, actually no, because then I have to start dealing with white space, and I don't want to have to deal with white space yet. Pretend I said anything. So cool. We have statements. So let's make a more interesting statement. Let's try making... I was going to say let's try making, like, conditionals. But then I'm going to need to start messing around with types. So let's add basic type checking, and let's add integers and booleans. So we're going to go down a bit of a rabbit hole now, but we're going to have to do it anyway. So here we go. So we're going to have a type checker, and it's going to have the same pattern as the others. It's going to have an expression package, or expressions, I guess, if we want to be consistent, and a statements package. And so for these typed expressions, I kind of don't want to have everything prefixed by typed, but I guess I have to distinguish it between the old and the non-typed and the typed, but it's fine. So actually we want to have a typed expression class, which is abstract and sealed, and it commits the typed binary expression just so we can get it compiling, and this has to be final. Make it, yeah, and this also has to extend typed expression. Cool, cool. So this has, so yeah, we are going to have to kind of like duplicate every expression kind, but I think that's fine. I suppose. And then I think we're also going to have a typed, not a Kotlin file, but we're going to have a typed binary op. And there's going to be a good reason for this, and I think it's going to be a class. Yeah. Yeah, you'll see where I'm going with this in a bit maybe. Okay, so it has these three things, and then we need getters for all this shit. Okay, so the reason this can be a class is because the same operator could have different types depending on its inputs. So a plus between two integers will give you an integer, but that same plus between, or at least that same like token plus between two strings gives you another string because it concatenates the strings. Or that plus, obviously, between like two floats would give you a float, not an integer. So I think we need some way of encoding that. So what was this? Yeah. Yeah. Damn, we're going to go down a bit of a rabbit hole here. Okay. All this just to implement if. But that's fine. That's the goal of today's, I was going to say stream. I'm not streaming. I'm just sitting in my office recording myself. The topic of today's, or at least the goal of today's video, is to get if working. So for that, we're going to need all of these things. So we also have a typed int. I guess this is a typed literal expression. Maybe. Because then it can compress all of the... I wouldn't have to have one for every kind of literal. I wouldn't need one for a float literal, an int literal, a bool literal. Although maybe it is easier if... Yeah, it's easier if they are separate. It's fine. We're not paying by the class here. So you have a value. That's kind of it, really. You don't need to have a span. So when you're type checking, I don't think you really need the span so much. Because when we get into the next stage later on, which actually we may need to do for ifs as well. Damn, okay, this is just smashed open my compiler. Which is lowering. So inside Java bytecode, there isn't really an if operator, or like there isn't a bytecode instruction for if. There are bytecode instructions for jumping, which lets you implement if, but you have to take your high-level if structure and translate it into a sequence of like jumps. So we might also need to do that. Okay. This video got a lot bigger than I... In my head I was like, oh, I'll just implement statements and then we can end with an if. And then I didn't really consider how much I would have to implement for if. And I would have to implement even more for while. But once we implement if, adding while is really easy. So maybe we could do that at the end. I'm promising a lot and I'm not coding. Let's keep going. It's a typed expression. We add that as a permit. That has that. And then we want to get the... No, we want to get the value. There we go. We got that, and we want to have a typed... Do we want a typed parenthesized expression? I don't think we need one, because we've already worked out the structure in the parser, so we have one less expression here. Cool. And then we're going to have a typed expression statement. We also want a typed statement class. And again, we do the same trick. Sealed abstract type statement permits typed expression statement. And you are final. And you extend typed statement. And you just have a typed expression. Like so. Nice and easy. So, our type checker. Well, we also need to have the concept. In fact, let's just do it like this. The concept of a type kind, which I think is also going to be a class. No, this is going to be, let's call it a Jura type, because I think if I just call it type, is type a... Type isn't a reserved keyword in Java, is it? I think I'm going to keep it as Jura type to distinguish it from Java types or like JVM types later. So I think that's useful. And then this is also going to have a type kind. Or maybe we do the same trick. Let's keep doing it in the same style as like with sealed abstract sealed And so this might be overkill. Let's say int type. Let's try this. Extends Jura type. Public final. So what does a type need? I guess you would have something like abstract boolean is assignable from, something like that, and then you would have some other type. Something like that, but we don't need to worry about that right now. And now we're going to add a boolean type. Yeah, I'm already kind of not liking a class per type. But this might get better in future because later on you're going to have something like array type, which is going to have a Jura type in it, and that Jura type in it can also be an array type. Or you'll have a class type, and that class type has in it a list of types which are its fields, and maybe you have like a method type like that. I don't know. Let's just keep going this way, and if it ends up really awful, I can just change it. Cool. So, a typed expression. The important thing about a typed expression is it has a type. So, in fact, no, it doesn't need to be constructed. In fact, no, you don't need it to be a field. You just say abstract Jura type, get type, like so. So every implementing subclass tells the compiler what type it is. So for this, rather than returning a new int type, so I'll take final int type instance. Yeah, the cracks are starting to show with this strategy. This is a bit wonky. Let's keep going, but I'm already not enjoying it because there's only ever one int type, but if we have something like array type, then there's different array types per whatever expression. And if you have like class types, there's as many of those as you want. Let's keep it like that. So then the binary expression. This one's interesting because the output of this is the binary typed binary op. Maybe we do the same thing. I don't know if we actually have to do it all in different files. Let's try this. So let's say public final class. Let's say add extends typed binary op. Oh, I don't have to say it permits it if it's inside the same file. Interesting. So what we're going to have, we're going to have a public abstract Jura type, and it will be, what would it be called? I guess get result type, and that would have a Jura type left and a Jura type right. So if you implement that, can I do switch left right? Is that something I can do in Java? Of course not. Of course I can't. That would be too nice. So let's switch left. If it's Boolean, throw new illegal state. I don't know. I don't know, man. Something like that. And then switch right. See, this is why I wanted to have the combos. Because this is going to explode. Yeah, there's got to be a better way to do this. Maybe we have a left, a right, a parsing binary op, and then a result. And we have a constructor. Yeah. And then we don't need that. Then we could have like a private static final add. Maybe an array. Trying to remember how Immo Landworth did it. Basically, I'm thinking we have like a list, or like a static table of what types can be applied to this binary expression. So let's just call these adds and do this. So we have a new add. Well, this needs to match the that. It's going to be private. So this is maybe int type instance. So yeah, we could just do this here, and then we don't need to do any of this crap. Okay, alright, here we go. We found the solution. And then this can be private. So add. Boom. You can add two integers, and that gives you an integer. I hate this instance thing, to be honest. I don't like that one bit. But hey, so then we need to do sub, mul, div, and rem. And then we need to have a public static typed binary op. Say check. And then we're going to have a Jura type left, Jura type right, oh, and a, I can never remember and an op. There we go. And then we just say for typed binary op, typed op in ops. If typed op left equals left, and type top up equals up, and type top right. God, this feels real wonky. Return type top. Otherwise, throw new illegal state exception operator blah is not applicable between blah and blah. Something like that. That's not how you do that. That's how you do that. Okay. Whatever. And that's what we're doing. Okay. So now our typed binary expression can have a typed binary op. What the hell are we doing? Okay. Our type checker. Our type checker gets a list of statements, and it basically just does the same thing that the emitter does. Now we can just say public list, type statement, type check. We just say list of typed statement, typed statements equals new array list. For the statement in statements, we just type check a statement. So we just say type statements, add type check statement. Not like that, but like that. To return those. So type checking a statement, we need to just switch on the statement. We only have one kind of statement, which is an expression statement. So we want to return, or we want to get a typed expression. Let's say typed expression equals type check expression statement expression. Yeah. And then we want to return this, yield new typed expression statement with that typed expression. Like so. This we want to return switch on the expression, and here's where we actually start to do the type checking. So for this one, int expression, well this is just a new typed int literal expression, which takes the int value, easy. Parenthesized expression is just type check the parenthesized expression's expression. So the binary expression is actually the interesting one. So we want to say var LHS equals type check the binary expression's LHS. The RHS is this one's RHS. The op is the binary expression's op. So then we say the typed binary op, typed op is typed binary op check LHS get type op RHS get type. And we can just yield a new typed binary expression with the LHS, the typed binary op, and the RHS. So all that work was for that, and we don't need a semicolon there. Just like that. Wow. That was actually easier than I thought, and now I'm scared to run this. I mean, we only have one type at the moment. We have Boolean, but we never instantiate it. So now our emitter, here it is, now needs to work on typed statements. Which is very easy because you can just do this, and now this has to be a typed expression. Typed binary expression. Typed int literal expression. And now we no longer have any parenthesized expressions, so we can get rid of that. So we're simplifying there. Cool. So then this op. Yeah, we need to do like get op, get op. But we now have more information here to do. Handle the typed op. Because if this op is saying we have floats, it's an add between floats, we don't want to be doing the integer bytecode. We want to then switch and say, okay, well this is now the float operators. But we don't have those yet. So this should all still just work, except we don't actually do any type checking. So we want to basically do this exact same thing. So we want to say type checker is a new type checker with the statements. And then we just want to copy this pattern. Type statement, type statement, type statements. Type statement, type statement, type statement, type checker, type check. Oh wait, I do it as a list, so I can just say type checker, type check. I don't know why I don't just do the parser like that. That would be much nicer. Failed. Operator mul is not applicable between null and int type. Ooh. Interesting. Methinks I forgot to do this. So typed expression get type is null. It actually is the result of the op. There we go. So yeah, that's how you type check the binary expressions, is their result is just the result of their op. So say if the left hand side was integer and the right hand side was float, for example, then the typed op would know, okay, I need to return a float because that's that's how I wouldn't lose any information. Or like maybe we would force a cast, depending on how we want to handle this in the language. The op result would tell you, okay, this returns a float. So we should see no difference. There we go. But now we have types. So I think it's time we add booleans. So I'm going to take another quick break and then we're going to add booleans. Okay, second coffee of the day has been acquired. Let's add booleans. So this is actually kind of interesting because now we get to add a new type of token. If I could just find my lexer. There it is. So we have this is how we do our lexing basically. We look at what the token is, what the character is. And depending on what the character is, we either say, oh, we know what that is, it's one of these, or we say, oh, we don't know what that is. Let's see, is it a digit? So now we need to also say, oh, if the character is alphabetic, and then we yield lex identifier or keyword. So now we need to have like a list of keywords in our language. Let's put them right at the top. As a final one of these. Or we could be a bit more rough about it and just do this. So lex digit, kind of the same pattern. We just say if is or what was it? Is letter or digit. because we can have a identifier that then has a number in it, as long as it begins with a alphabetic to trigger this method call. So you could have something like var my variable 123. That's a valid identifier. So we'll call this identifier. Well, it's a letter or digit, and we append it, and then we say call it text. Do this, and then we say, can I switch on a string in Java? I can. Haha. So then we do this. Token kind is going to be, let's put it up here because it's one of the more important ones. Identifier. We don't care about that one yet. We have a true keyword and a false keyword. Those are our two. Well, no, let's keep the default so we can do this. So this is it like that? Yeah, it is with an arrow. How weird. It is an identifier with the text and the text length. We don't need to say return. If it is true, does that work? Oh, I need to say case true. We say new token, token kind, true keyword, and then same as this, to be honest. Why do you hate this? Different case kinds used in the switch. Ah, it all has to be an arrow. Okay, whatever. True that, false that. Something like that. So this is where our keywords are going to be stored for now. So in future, we'll like when we get onto it, we'll have if and so on. So let's make a program. Or like that. This is going to shit everything up because it's not going to know what to do. Unexpected token, true keyword. We need a new kind of expression. A bool expression, which is just an int expression but with a bool in it. Like that. You need to be final. Final. And I've got an extra semi. Not an extra semi, an extra curly. Cool. Easy. Now we need a typed bool literal expression. Let's just say, yeah, it is a literal. So really, those ones should be called a literal. In fact, let's do that, because a bool expression could be anything that returns a bool. This is explicitly a literal. Same for this one. There we go. Typed bool literal. Why? That's just the same as a typed int literal. What's the difference between final and sealed? I don't know. And then we just yoink all the stuff from here. This is now a boolean. This is that, this is that, this is that, and then this is the bool type instance. Boolean type. I prefer expand. I prefer bool to boolean. Like in my language, I think instead of the keyword being boolean, it's just gonna be bool, just because it's nicer. And we are going to do the same thing as this. There we have that. Boom. So now we've got a typed Boolean expression. How about that? And then our type checker is complaining because we have a new type of expression, so it no longer compiles, which is exactly why I like to have these sort of exhaustive switches. To make the missing case, and this is just a new type bool literal, and we take out the value, and that's that. And now my emitter should be complaining, which it is, because now it doesn't know how to emit a Boolean. So we want to probably put this on a new line and say mv visit int instruction. And is it a bi push? That's a byte. Typed bool literal get value. Is it visit? Yeah, there's no visit bool because I think booleans. What would it be? It might just be visit instruction. Is there just a true or... Let's consult the holy texts. The list of Java bytecode instructions. Sorry for the flashbang again. So, these are all of the bytecode instructions. I want to know how to push a Boolean. There's a byte or a Boolean. Yeah, those are boxed Booleans. So I think we just push a byte, and then the JVM just knows what we're doing. Yeah. Oh wait, there is I remember there's a push for a 1 and a push for a 0, so you don't need to use the double or like you don't need to use 2 instructions. Where is it? Not iStore. Am I wrong? There's got to be an instruction that's just pushing a 1. Yeah. Decon 0 is a constant 0. We could just do by push for now. I swear there was like a... Is there iconst? Is that what I'm thinking of? Yeah, iconst. That's what I'm thinking of. So visit instruction. Can I just call it expa? Can I call them all expa? I can. Nice. So expa get value. If it's true, we do iconst 1, else we do iconst 0. Cool. I think that's how you do booleans in JVM, in the JVM. Let's find out. Why do you unexpected token true keyword? I never parsed this. Not that. True keyword is bool literal with true, and a false keyword is a bool literal with false. There we go. So what happens when I run this? Yeah, it prints 1. I know why. Because we're telling it it's an integer. Because when we print, the way we do the print is we have to have this descriptor. And that descriptor tells you what signature of the method to use. So we're using the overload of print stream print line that takes in an integer and returns nothing. So instead, if this is scuffed as all hell, by the way, this is horrible. I take the expression statement expression type. Am I allowed to do that? Yes. If it's an integer, we invoke this one. If it's a Boolean, I can't remember the descriptor for Boolean. I want to say it's just B, but I don't think it is. Java bytecode descriptors. Here we go. Z is a Boolean for some reason. Okay, so now when I run it, prints true. So the reason that works is because if this expression is a Boolean, I'm saying call the overload of print line that takes a Boolean and returns void, and then the internals of that overload knows that it should print true, not 1. Cool. Do I need this? Does that work? Is that a bad thing? No? Okay. Cool. So if we go back to our program, eventually I need to make this just accept a file. We can also have false. Amazing. We have Booleans. Cool. So I think we can finally add ifs. So let me delete all of this and say if true. I don't want to fuck around with curly braces. If true, 5. Oh, this is horrible. I need to have better. Like expressions. Like I need to have an actual like print statement. Who cares? Who cares? This is fine. This is going to be a valid statement in our language. So this is immediately going to explode. Yeah. Unexpected token identifier. Well, yes and no. This isn't an identifier. This is an if keyword. So let's put that down here. And we go to our Lexor. And now we say if keyword. So now it should complain that it doesn't know what to do with an if keyword. Bada bing, bada boom. So, our parser. Now, we finally get to do something interesting in our parse statement. In fact, let's call that parse statement. And let's do public list statement. Statement parse, and just say while cursor less than token size. Getting sidetracked, but this is going to be much nicer. Statements, add parse statement, return statements. And then in Jura .java, we can just say that. And then we'll do the same for the Lexer as well, eventually. Parser, parse statement. If we have case if keyword, now we start doing stuff that's actually interesting. So we we say expect next token kind if. So that gives us our if keyword. Then we expect an expression. And this is our condition. And this is going to be parse primary. Does primary call binary? No, binary calls How does this do it? Yeah, it has to be binary expression. Okay. Notice I do not expect brackets. I don't expect parentheses. This will implicitly check for parentheses because we have a parenthesized expression. So parentheses are optional in if conditions because this language is better than Java. And then statement body is our statement. That's it. No else at the moment because that makes things complicated. So that is it. And if anything is unexpected, those calls are going to throw an exception. So we just return, no we don't, we yield a new if statement with the if keyword, the condition, and the body. Let's add it. If statement extends statement. Implement the methods. Add it to that and make it final. And then add a constructor. Create fields for all of them, please. Sure, let's have that for these. I don't think we need to get the if keyword. And then a span from the if keyword to the body. There we go. I think that's it. So now if I run it, this type checker is like, well, hang on, how do I type check a if statement? Well, you first of all type check the condition, and you let's call that condition, and you type check the body. And then you yield a new typed if statement with the condition and the body. But this condition has to return a Boolean. So if a condition get type does not equal not like that. Like that. Throw new illegal state. Condition of if statement must be of type bool. Cool. And so we now have not an expression, oops, but a new typed if statement. Like so. And then we just want get condition, get body. Okay. So here is where I would add lowering if I could be bothered. But this video has been going on for quite a while, and I just want to compile this. So I think our bytecode emitter is going to just do a bit more heavy lifting than we want it to eventually do. So how do we do this? So we have to emit the condition. Let's go back to our reference of bytecode. So I think it's called like JMP, what is it called? Which one is it? I mean, there's goto, but that's unconditional. If. Okay, so there are ifs. I think we're only going to care about if ec. So if value is 0, branch to instruction at branch offset. Are there labels? There aren't labels. So you basically need to tell it where to jump to. So if ec branch byte 1, branch byte 2. Yeah, so we basically need labels, I think. What does it look like in here? If I say mv, yeah, you visit label. So yeah, there aren't labels in the bytecode, but there is in this. So we emit the condition. We have a label. Let's see, what do we have in this side of label? Okay, well so this will be if true, and this is going to be if false. So we emit the condition. We visit if true. Let's visit if false. And then here, mv, nope, we emit the body. So basically what I'm trying to do is say, I need the method visitor. So I'm going to emit the condition, which will resolve to a Boolean. But inside of the JVM, those are just integers or like bytes or whatever. And I want to say, is that equal to 0? If it's equal to 0, that's false. And I want to jump to if false. So let's say mv, someone's banging some metal outside, sorry if you can hear that. That will be visit, which one of these would it be? I think it's just visit instruction or visit in instruction. Oh, visit jump instruction. So this will be if ec. So if it's equal to 0, we jump to if false. So I don't think we even need if true. Yeah, something like that. Maybe. And then this should all be like lowered into a sequence of like labels and jumps. So we don't have to implement if, we don't have to implement while, we don't have to implement for, or like for each, or ranges, or all of that stuff, because it all gets lowered, and then inside the emitter we just say, oh, we know how to handle a label, we know how to handle a jump, we know how to handle all of this stuff. Does that compile? Somehow it does. If we take a look at the decompiled bytecode, if true, print 5. And if we look at our original program, again, very loose, we're saying if true, 5. So if I run that, it prints 5. I can get rid of the parentheses because I don't mandate that we have to have parentheses. It still prints 5. If I say if 10, we get an error. Condition of if statement must be of type bool. And there we go. We have ifs. We have really, really bad ifs. And we could even do something like this. If 10 greater than 5, 5. So let's implement, as the last trick of this video, some simple Boolean comparisons, or integer comparisons. So this is going to break because it doesn't know what the hell that symbol is. Unexpected character there. So we go to the token kind. We're going to add a bunch of these. So this will be an open angle, a close angle, a close angel. I'm not going to bother with equals equals or exclamation mark equals yet, because those are like 2-character tokens, and those we don't have easy support for yet. It's very easy to add, but this is just going to be a little collar at the end of the video. So we'll just have greater than or less than for now. So our Alexa, we need to add, this is an open angle, and this is a close angle. Sick one. Then the parser is going to say, what the hell, man? What is that? So we go to our parser. And first of all, we need the precedence. What is the precedence of the token? Oh, I also moved this into the token kind because then it's just closer to that. And I think it's actually less than these. Because if you think, if you say something like, if 10 plus 3 less than 2, yeah, is always false. It does the addition first, and then it does the comparison. If it did the comparison first, you would have 10 plus false, and that doesn't make sense. So I think it's nicer if the close angle is 1, and the open angle as well. Excuse me. Like that. So now they have a binary precedence. If we go back to the parser, so this has precedence, and this then has the 2 new ops, less than and greater than. Or maybe we should do greater than, less than, because it's alphabetical. So case, let's see, open angle, which is this one is less than, and so case close angle is GT. Where else are we going to complain? Operator GT is not applicable between int type and int type. Well, it should be. It should be. So we're going to typed binary op. Well, if we have int type less than int type, that is a bool type. And if we have int type greater than int type, we get a bool type. And then it compiles. And then it compiles. And we get 5 because 10 is greater than 5. What if we did 10 greater than 5 plus 5? And again, no parentheses, because our parser is smart enough to know what we're actually trying to do here. So we do that. Still prints 5. I would have expected it to have not. 5 plus 5 does not equal 0. 10 greater than 5 plus 5. You should have bound more strongly here. What if I did that and that? Does that change things? And that's still the same bytecode. Interesting. 10 greater than 5 plus 5. Open angle is less than. Yeah. So I did that right. What the hell? Let me see what we end up with. So our statements, we have one statement, which is an if statement, and the condition is a parenthesized expression containing a binary expression, which is 10 greater than I mean, that's still false. Hang on. You know for why? Because in our emitter, yes, in our emitter, we don't handle them. Okay, I'm going to add a default. Throw new illegal state exception, unhandled binary op, blah. This is something I wish the compiler did for me, but never mind. Binary expression, get op. So now if I try and compile, yeah. Unhandled binary op, a bunch of nonsense. If I get the actually underlying enum, we get unhandled binary op GT. There we go. I believe there is no GT. There is if I compare GT and if GT, but there isn't one that will consume them and then put it on the stack. So, first of all, get rid of all this nonsense because I was right. It was just ignoring this and then it was adding those together. So I think the easiest way for us to handle that for now is if we have GT, let's see. So I think we want to subtract. I think. Let's see. What does that do? Yeah, if 10 minus that does not equal 0, which it does, so false. So 10 is greater than that. And then less than would fail because we want to swap and then minus. So we get rid of that, get rid of that. LT, make some room. We want to mv visit instruction swap. I think. So yeah, if we change that to be 10 less than 5 plus 6, it prints. If we make it greater than, 10 is not greater than 11, it still prints. Okay, all right. Ah, because we're saying does not equal 0. So yeah, I think we need to do a lot of processing of this to use the correct if bytecode instructions. But for now, instead of saying if ec 0, we want to say if greater than or equal, and we want to visit instruction iconst 0. Something like that. Because now it will say yeah, it will say something like that because our bytecode is horrendous and it won't print anything because 10 is less than 11, but if we say it's if it's less than, still nothing. I think I need to use the compare if I compare ec, or if I compare greater than or equal. No. If 5 plus 6 minus 10 less than 0. Yeah, that should have worked out the precedence. There we go, that prints. 0 is less than... This is so stupid. All because I don't want to process the correct... Oh, there we go. So, yeah. If 10 is greater than 11, print 5. Doesn't. If 10 is less than 11, prints 5. Okay, that's horrendous. You know what? To do, this is horrendous. In the lower, emit, or in the lower, determine the correct if comp instruction. But for now that works. And yeah, we can have else and stuff afterwards, but eventually we want to have something like this, which is a block statement, which is just a list of statements inside curly braces. So you could have many things. But I think I've gone on far too long today, but we've accomplished a lot. Like, we have rudimentary type checking, we have booleans and integers, we have statements, and we have simple if statements. No else, but we have if. And I think next time we're going to implement the proper lowering for this, and implement block statements, and that way we can then very easily create while, because then that's going to have basically the same underlying structure as an if. So all a while loop is an if, so you just say this, and then the condition. The only difference is, instead of you just hit the end and you keep going, at the end you just have a go-to that jumps you back up here, or to the condition, here, and say if, and then if this is false, you jump past it. That's all a while is. It's just a spicy if. So, thank you very much for watching through to the end. I understand this is probably not the most thrilling content, but I'm enjoying myself, and if you're enjoying it as well, give me a like, give me a subscribe, give me a comment. If you hate it, give me a comment, tell me why you hate it. All that engagement's good, baby. And I hope to see you again on the next one. So, thank you very much for watching, and bye-bye.